Hi folks, I've noticed that we're still having some minor trouble with using the computer algebra system within GeoGebra to make some computations. I just simply want to show you that if you follow the notes and follow the book, many of these computations are fairly straightforward. I'm going to be doing the work that's in this assignment called dot products of plane vectors. We're going to do four things. We're going to use the dot product to figure out when these two vectors are perpendicular, which is a pretty simple thing. We're going to use the dot product to find out what might it be that occurs when the dot product of these two vectors is equal to 5. Then we're going to find the length of a vector using the dot product, and finally we're going to project a vector 3, -4 onto the vector 3, 2. Okay, so getting started with GeoGebra, I need to make the two vectors T4 and, oops, sorry there, I don't know why that's going, and the vector 9t, and I'd like to know when is their dot product 0, so I'm going to solve the equation dot vector 1, so that's the vector in box 1, $1 refers to the lines in the CAS system. Dot 2 equals 0, and we're solving for t, and we get t equals 0. If you'd like to actually see the dot product is 13t. I think that's pretty easy to compute, and most of you should be able to see that. Next, what does it mean to say the dot product of two vectors are 5? Well, if I put those two vectors in, vector 2, -3 and xy, and then I take their dot product and set it equal to 5. So I'm going to dot 4 with 5 and set it equal to the number 5. So what is that? Well, I think we all recognize that as points on a line. So I can plot that. We've seen that in a previous problem. So one way to think about dot products, dotting with a specific vector, gives you all of the vectors that whose heads lie on a specific line. Not that that's overly important, but that's one geometric way of thinking about it. Next, how do you find the length of a vector? Well, the length of a vector has to do with dot products. Or one way to think about it is dot products. So the vector 3, -4, if I'd like its length, that's just the square root of, oops, sorry, better fix that. So I need the square root of the dot product of 7, vector in number 7 with itself. That's the one way to find the length of something, is dot it with itself and take the square root. And of course the length of that is 5. And I think if you drew that vector in standard position, you'd certainly see the legs of a 3, 4, 5 right triangle. Finally, we have to find the projection of the vector 3, -4 onto the vector, and I'm going to go ahead and type it, the vector 3, 2. So I want to see what part of this vector lies in the same direction as the vector 3, 2. So I just want to make sure we're all on the same page with this work. You know, if you're reading along in the textbook or in the text resource, I'm talking about using the formula here on page, let's see, that's page 23. So it looks right here, projection of A onto B. It's A dot B divided by B dot B times B. So if I use that formula, I'm going to go ahead and say the dot of the vector I'm projecting, 7, onto the vector I'm projecting onto, which is 9, divided by the dot product of the, oops, cancel, the dot product of the vector I'm projecting onto with itself times that vector. And so there you have the projection of the vector 3, negative 4 onto the vector 3, 2. It's just a little tiny piece. I think you can see it. It's 1/13 of the length of the vector you're projecting onto 3, 2. And if you drew this in space, I think you would see quite clearly. There is the vector u. Here is the vector v. And if I project one onto the other, it's a little tiny piece. So the part of the vector 3, negative 4 that lies in the same direction as the vector 3, 2 is this small piece right here. And that's how you might compute it with the CAS. Thanks a bunch, and look forward to seeing more of your work.